aldols. Right? What we've got here is a mixture of sodium hydroxide and an aldehyde. Okay? We've seen this already. We saw this reaction start to happen. Okay? The very first thing that we should go through and do is decide what is the most reactive thing. That most reactive thing is going to be the most polar bond. The most polar bond is? Nope. Is our ionic bond. The ionic bond is between a metal and a nonmetal. Our most polar bond is actually between the sodium and the ethoxide, giving us a negative oxygen. I need to stabilize that negative oxygen by finding something positive. Where is there something positive? The carbonyl carbon. So that negative can attack. We break the carbonyl carbon. We'd have O minus, we'd have OET, we'd have our hydrogen. That hydroxide, or the ethoxide, believe it or not, is in the presence of ethanol. So that is also present. So we could have this reaction happen. What would we end with? What is that structure? This is a hemiacetal. Okay. It could keep going. This is basic conditions, and under basic conditions, we can't continue forwards. Okay. Under basic conditions, the hemiacetal is as far as we can get. We can't continue on to the acetal. For review, go back and watch the lecture on acetals. Okay. Is the hemiacetal a stable structure? No. Okay. That hemiacetal is in a very strong equilibrium that favors the carbonyl. The acetal-hemiacetal path is absolutely still possible. Okay. So if we're looking at yields, we've got a problem because the acetal-hemiacetal formation is going to reduce yield. Okay. But it still does favor the carbonyl. Okay, so it's not a large driver of our product formation. So now the question is, well then, what the heck did the ethoxide do? If it didn't go through to attack the carbonyl, to go through and form a hemiacetal, how did I stabilize it? What does it need to be stabilized? It needs a positive to stabilize that negative. Where is there a positive? An acidic hydrogen. Okay? Well, if we go through and evaluate these, there's two types of hydrogen. We have the blue hydrogen and we have the purple hydrogen, right? Those other hydrogens are all the same, so we won't worry, or the same as the purple hydrogen, so we won't worry about that. So we try and decide between the purple and the blue, which one's the most acidic? 9 times out of 10, what do you say? The blue one. And why? The electronegativity. It is closer to that electronegative oxygen. That argument that you're making is not electronegativity. That argument that you're making is induction. Induction is the last thing on the list before you're like, oh my God, I really don't want to have to evaluate that. Right? Are there things that are more important than induction? Yes. Should you evaluate those first? Yes. If we look at the results of removing the purple, we would end up with a negative carbon. If we look at the results of removing the blue, we end up with a negative carbon. Okay, so if we go through and use our charge rule, the charge is the same. We use size, it's both carbon. We use electronegativity, it's both carbon. Now we have to move to resonance. Okay? In the process of moving resonance, I can take a pair of electrons and I can move them someplace that is lacking. Okay? That's not obvious to see here, but what I can do is move those electrons to that bond. What happens to that carbon now? It would exceed the octet. It is okay to exceed the octet in a transitional structure. Okay? Not okay to exceed it at a final structure. Okay? So because it's exceeded, I need to move a pi bond. So I will move said pi bond away from it. What is the result? We would end with the enolate. I now have a negative charge on oxygen. If I look at those two purple drawings, which one should I be evaluating stability based off of? Of the purple ones. The oxygen one, not the carbon one, because oxygen can stabilize the negative charge better. If I want to know something about how this molecule reacts, I'm going to look at the carbon one because it's less stable. It's the first worst resonance structure. Okay? Let's go through and take a look at the blue. Where do I move those electrons? Okay. Well, you just move them towards the oxygen. Okay, let's move them towards the oxygen. Okay. What happens if we do that? 1, 2, 3 bonds. There's the oxygen. Okay. Everybody says, oh, we can't have a triple bond oxygen. Yes, we can, but we can't do it this way. Okay. What is the problem with this triple bond?
It's got 10 electrons around.
That oxygen has exceeded the octet. Okay. Again, I'm allowed to exceed the octet in a transitional drawing, not as a formal drawing. So I could recognize, oops, I'm going to exceed the octet up here. I need to break a pi bond. Okay, well, there's a pi bond to move. So let's move that pi bond. Which way do I want to move that pi bond?
Towards the oxygen.
Towards the oxygen. So let's do that. Okay? Because clearly, Mike, we weren't going to make that mistake. We knew your game. So let's fix that. So if we now look, we still have the double bond, right? Yeah, because the blue electrons, the lone pair from the carbon, went up to make that double bond. And then I broke the double bond that was already there and added those electrons to the oxygen. So come on, Mike, what's the problem with that structure? It still exceeds the octet on the oxygen. Still an invalid drawing, which means those arrows don't work. Try whatever you want to. No resonance. Which is more stable? Negative carbon, negative oxygen. Negative oxygen. The aldehyde hydrogen is not acidic. Okay? If we go through and look at what an aldehyde is typically presented as, it is almost always presented as shown now, okay, without all the hydrogens drawn on it. Okay, and then we throw a base at you. You're like, base. What do bases do? Take away hydrogen. So what's your instinct? Take away the hydrogen. What hydrogen? Well, there's only one hydrogen shown, so I'm going to remove that one. Exactly the trap we're setting you up for. Okay? Don't remove the obvious atom. Pause and just think, just a little bit, like, am I getting set up? Okay? And in this case, yes, you're getting set up. Whenever you're doing an acid-base reaction, you need to think that you're removing hydrogens. Well, what hydrogens? Typically, we imply hydrogens, which means you might need to draw on all of the hydrogens. When should you have had that practice so that you knew not to draw all the hydrogens? Very beginning of first semester. Right? That application is now coming back and biting you if you didn't get used to those implied hydrogens. That's okay. Right? All we're trying to do is point out that we did try to teach you that, and it didn't stick. Not everything's going to stick. That's okay. But you do need to acknowledge that now. Otherwise, you will end up having a hard time with the aldol reactions. Okay? So the hydrogen that we remove, is out at the end. If we now evaluate the two structures that we drew below, what's the word? Below. Sorry. Just didn't come to me. Which of those resonance structures should I be using or evaluating to continue my reaction? The more reactive one. Which of those two structures is more reactive, A or B? A. So I now have a nucleophilic carbon. This goes all the way back to Unit 1 of this semester, thankfully, just this semester. Okay? And we talked about what would happen if we take ethoxide and reacted it with an aldehyde or a ketone compound and removed a hydrogen. Okay? And we said that that is not a stupidly strong base, which means we only deprotonate some of the starting aldehyde. Okay? Why does that become important? If I only remove some of the starting aldehyde, the end of this first step, I actually have two things present. I have the purple and the blue structure. What is the purple structure? Yeah, an enolate. Keep going. It was a horribly vague question, I know. A nucleophile. What about the red structure? It's an electrophile. Okay? Right at that carbon that we initially tried to do and went down the acetal pathway. That acetal pathway that didn't go anywhere. Okay, why not? Well, it had to do with oxygen's reactivity. Have we changed the atom that's attacking the electrophile now? Yeah, now it's a carbon, not an oxygen. Is that going to change the path? Well, I don't know. How would I know? I draw it out. So I'll take that negative and I'll attack. That pushes the electrons up because I would exceed the octet on that carbon. What's the result of that? So there's the purple structure. I now formed a new bond between that carbon and that carbonyl structure. Yeah? Everybody see that? That red oxygen would now be negatively charged. That's not stable. So what could I do to stabilize it? Could add a hydrogen to it, protonate it, so it becomes stable. Where do I get that hydrogen from? Ethanol. That ethanol that was implied in the solution that we didn't explicitly... Yeah, that one. Sorry. But yeah, that's where it's coming from. And what do I end with? Sorry, I should have just erased all the boxes from the beginning. What would I now get? That structure has an alcohol in it and an aldehyde. What do chemists do when we have multiple functional groups in the same structure? We invent a new name. Okay, what's the new name we invented here? Aldol. Aldol. Okay, because it has an aldehyde and an alcohol. Does this still work with ketones? Yes. Less effectively. Why? Hint. Why is a ketone less effective as this? The ketone is less electrophilic than the aldehyde because the extra carbon that's there donates electrons in to stabilize the carbonyl carbon. So the ketone becomes less active or less susceptible to this. We saw this reaction happen very frequently with aldehydes and just common storage containers. Ketones don't have as much of an effect. Okay? They still run the reaction, the same core reactivity. We deprotonate, nucleophilic addition, we protonate, we have a carbonyl and an alcohol. Officially, if it was a ketone, it wouldn't be an aldehyde and an alcohol. It would be a ketone and an alcohol. So we might call that a ketol, right? That just sounds stupid and could be confused with ketal, which is something else, right? So we just refer to the chemistry in general as aldols, okay? Turns out that this structure in and of itself is also not all that greatly stable either, okay? So what can we do to help with that? Okay, or where is that stability issue? The oxygens are near each other. I would actually argue that that hydrogen could hydrogen bond to that, which would actually stabilize that. What kind of conditions were we under? Basic conditions. Okay? And if we're under basic conditions, before we start stopping reactions, we should probably consider, is there anything more acidic in solution? What about the aldehyde?
More basic. No, never.
Remember that hydrogen we removed at the very beginning from our aldehyde? It was acidic because we had that resonance stabilization, right? Do we still have those alpha hydrogens next to a carbonyl?
Yes.
Yeah. So those could still be acidic. Are they more or less acidic than where we started?
More.
Why? Why are they more acidic? No, it has resonance here. It definitely doesn't have resonance that way. So I don't accept resonance.
The extra carbon? The extra oxygen?
What about that extra oxygen?
Electronegativity?
It is electronegative. So now the difference between our aldol and our starting aldehyde is the aldol has an inductive effect, making those purple hydrogens more acidic. So what happens?
It keeps going.
It's going to continue to react. Okay? And the first question that might come to mind would be, well, that is now less stable because it is charged. And you are absolutely correct. What could we do to stabilize that negative? Resonance would stabilize it, but that's why we removed the hydrogen. What could we do to permanently stabilize it?
Attack itself?
What do you mean attack itself?
I thought the negative was...
Fission? That's okay. What do you have? Let's take those electrons and let's make a pi bond here. This isn't resonance. We're now making a pi bond. It's not resonance because what would happen to that carbon?
You lose a hydrogen?
If I try to make that pi bond, what happens to that carbon? It would exceed its octet. So again, it's not bad to acknowledge that yes, the octet is exceeded, but we can't draw that as a result. So what would we have to do? We would have to eject electrons from the structure, okay? Or we have to eject a pi bond, in which case it's resonance. It's not resonance because there's no pi bond. Do I have a bond that I could break?
The OH.
I could take that oxygen and shuttle those electrons out to it. What does that mean I did? I eliminated it. But that means I eliminated hydroxide. Is hydroxide a good leaving group? Under these conditions, okay, in an excessively basic environment, it's not a great leaving group, but it's not horrible. Okay? So it is allowed to happen. What else really helps this reaction along? The conjugation of the pi bonds. The conjugation increases its stability or lowers its energy. Okay? That conjugation is what facilitates that elimination reaction. So if we break this down, our very first step was a nucleophile addition that resulted in an aldol product. So we call it an aldol reaction. Why don't we just call it a nucleophilic addition? I don't know. I completely agree. Calling it by what it actually is makes a lot more sense than making up names. right? But it's called an aldol reaction. That aldol did what? Once we made the aldol, what did it then continue to do? It dehydrated, okay? It was the loss of water. I got rid of a hydrogen and OH, so that was a dehydration. So beginning to end, starting with my aldehyde, ending with this red structure, I've done an aldol reaction and a dehydration. Okay? Dehydration is a bit narrow of a term. Could we expand that to something, say, that you're responsible for knowing? Could call it a condensation. It's the same thing as a dehydration. Condensation means I saw water come out of the reaction. What does dehydration mean? I took water out of it. Opposite sides of the same coin. It's an elimination. It's a nucleophilic addition followed by an elimination. Right? It's just a question of finding those categories so that you can pin things on them. Okay? If you decide to not pin according to those categories, that is your choice. But that does mean you're memorizing all those extra terms. Okay? Kind of makes sense? So, with that, if you download the slides, see all those little white boxes that are slowly disappearing, you can just kind of click and then hit delete, and you can delete those, and it'll show up all the stuff that was underneath it. Okay, so there we go. There's a nicer version of those drawings. So now what are we going to make you do? Practice. Now that we've shown the big, long way to go through and do this, let's go through and look at a potential shortcut. Presumably you like shortcuts? Yes. Yeah, okay. So we are reacting two molecules with each other. Okay? If we look, we're starting with one being a nucleophile and one being an electrophile. What is interesting about where I have placed these things? Exactly where the bond happens. And what happens? The nucleophile attacks and does what to one of those oxygen bonds?
Kicks it out.
Kicks it out. Then what happens? It protonates it and eliminates. You're like, dude, that's ugly. That looks nothing like that final product that was shown down here. Yes, it does. It is the exact same drawing, just flipped in a different orientation. Okay? So we have a way to kind of cheat our process through that. You have to be careful with cheats or shortcuts because you can run into problems. Those problems appearing in the very next slide. So let's go ahead and start with the first one. If we go through and run the cheat, number one, we should recognize that it's going to suck. Yeah. Right? Yes. Okay. So if we attempt to run the cheat, oh, wow, I can't even draw it. That's how ugly it looks. Okay, because I'm trying to get that nucleophilic carbon aligned, right? And then I'll draw my electrophilic carbon underneath and hopefully not lose carbons at the same time, right? And then what do we do? What did we say our cheat was? We connect them up, we delete, and then we connect them up, and we delete. And we'd be like, done, aldol condensation. That's horrible. That's horrible, yes. Why is that horrible? And not because it looks ugly.
It kind of looks like it.
That carbon has exceeded its octet. So if you go through and run, you say like, oh, that's an aldol, I'm just going to do and please don't ever call it Mike's cheat, but I'm going to say that. I don't want my name affiliated with it. That's really what it comes down to. Okay, run Mike's cheat for condensing those. Okay, you get the wrong answer. Okay, so if we adjust the cheat a little bit, and instead say we put up the alignment, we make one bond, we delete one bond. And now what we have to ask is, to make that bond, initially, we had to remove a hydrogen. There was a hydrogen there so that we could make that connection, right? Is there a second hydrogen at that carbon? No. If there's not a second hydrogen, I can't remove the second hydrogen to do the condensation.
So it stays now.
So what happens is it stays with the aldehyde and the just oxygen? I can't have just floating oxygen.
Sure you can.
So it just
And I get the aldol.
so it doesn't
Okay?
And it stays with it on that? Or does it pull
A lot of that is going to depend on mechanisms and how far they're expecting you to go. If we're drawing it like this, you'll probably see the aldol as an answer, and you'll probably also see the god-awful elimination as an answer too, and then a bunch of other random stuff.
Because what I did was I put the double bond to the other.
Yeah.
Well, if you do the double bond, let's green, you're saying in here?
No, to the other ring.
Here?
Yeah.
So you had to remove that hydrogen to do that?
Yeah.
Why is that hydrogen acidic?
There's an oxygen.
So an inductive effect of an oxygen. When we go through and look at this compound, are those hydrogens acidic? No. So I know what you're trying to do. You're like, oh, it's just condensed because we should do a no. Okay. The chemistry has to support it. That hydrogen is not acidic. You can't do that elimination. So that pi bond is bad. We have to go back to that.
So it stays.
Okay? Yes.
Do we just wave our hands and say those are hydrogen? Like somewhere in solution floating around?
To protonate. So for those of you that missed it in the first 20 minutes of class, where did that hydrogen come from?
Ethanol.
When we have the ethoxide, to get the ethoxide into the reaction, it is in the presence of ethanol. Your solvent is going to have that hydrogen. Yeah. And it should be shown. Okay, it should be. Okay, you'll notice I didn't show it for any of these. It's not because I was intentionally being a jerk. It's because we tend to not show it. Okay, it just ends up getting ignored through here. Sometimes we're really picky about showing the solvent. Sometimes we're not. Sorry. That's unfortunate. Okay. If at any point you're like, what's the solvent in this? Ask. Okay, that's absolutely fair game. Even during the ACS final. Okay, how about the next one? We go to the right. Well, we just do the same thing again. This one's, wait a second, where would I have that hydrogen to remove? Well, there's only one hydrogen, so I must be removing this hydrogen. That hydrogen's not acidic. Okay? So there's two ways that this question could get asked in a multiple choice. The first approach is you see all sorts of weird answers, but then you also see this one. What are they saying? No reaction. Okay? Which is fair. That is one approach as an answer choice. Is there another approach that we could have done? Yeah? How could that have reacted? Could have attacked the carbonyl carbon, giving us what? The hemiacetal. If you see the hemiacetal path, guess what one of your answers is going to be? The full acetal. Okay? Well, which one's correct? The hemi or the full? Why the hemi? Under basic conditions, we can't do that second substitution, and the hemi becomes our answer. Good catch? Okay. Questions? So that one, we said it varies. You'd have to look at your multiple choice. So you would either go to the hemiacetal or you'd say no reaction.
But would they ever give you both?
No. Yeah. We wouldn't do both because that's now unnecessarily convoluting the chemistry. Okay. So how about the next one? The next one is actually set up in a way where you could potentially run our cheat to make sure we don't lose carbons 1, 2, 3, 1, 2, 3. We make the bond, delete the bond. Do I have another hydrogen there? Yep, there is another hydrogen, which means I can delete, pi bond. Cool, right? Questions about that? Okay, how about the next one? Oof, that's not a bad statement. Okay, this one arguably is actually okay for the cheat method too. We take our base and we need to remove the acidic hydrogen. Where's our acidic hydrogen?
On the aldehyde.
They're both aldehydes, so I don't accept that.
Sorry, aldehyde A.
Aldehyde A has an acidic hydrogen because it has, at the alpha position, 2 hydrogens that could be removed. Notice aldehyde B does not have an aldehyde hydrogen, or an alpha hydrogen, because if there was one there, we would have exceeded the octet. Okay? Which means the nucleophile is going to be aldehyde A. There's our nucleophile with the red dot. Our electrophile, our carbonyl, hydrogen. I get lazy and I would write a pH. We okay with that?
Yeah.
Okay. Make the pi, or make the sigma, delete. Do we still have an acidic alpha hydrogen? Yeah, so I can delete that one, make the pi, delete. Make the pi, right? Somebody got it. Okay. So cool. That's not too bad, right? So cool. Aldol's neat because we've now expanded the carbon structure. We went from 2, 3 carbons, whatever. We have more carbons in our answer. Let's just try that. I don't want to count all the carbons. What do we have? 3 and 7. So we ended up with a 10 carbon answer as opposed to the 3 and 7 that we started with. So we're making larger structures. That's kind of cool as opposed to just changing functional groups. Make sense? So the aldol is useful in that respect, right? But let's continue to push it. Sorry. Next. Oh.
Doesn't the other one reaction doesn't react the first
They said that for
Oh, legit. I forgot. What's the problem here? We made the assumption that A all became nucleophile with that base. Is that true?
Nope.
That's not a stupidly strong base, which means some of A is left over to act as an electrophile. Which means we could make that bond. Do I still have alpha hydrogens? I can make that bond. How many products do I get? 2. Okay? So the aldol does have some weaknesses. We have to be careful with what reagents we choose. So when we went through and did that one, aldehyde B couldn't act as a nucleophile. So that meant we only had one nucleophile. That's cool. But the base we chose was not super, super strong, which meant that aldehyde A is going to form nucleophile, but it will also have unreacted electrophile floating around, which means we get 2 possible products. Yeah? What happens when we move the next one down? Thank you for catching that.
4 possible products?
If we go through, what does our base get to deprotonate? Well, it needs to deprotonate an acidic hydrogen, an alpha hydrogen. Well, here's an alpha hydrogen. Here's an alpha hydrogen. Are their acidities different? Yeah. Significantly? No, which means how many nucleophiles do we have? 2. Okay? Because we used that weak base, we have some of those starting materials also floating around not as nucleophiles. They'd be electrophiles, which means how many electrophiles do we have? 2. 2 nucleophiles, 2 electrophiles, we get 4 possible products. I don't want to draw them all. Okay? Make sense? What happens when we move to the next one? What did we do to try and minimize that? So what's the difference between the last reaction we talked about with colors and this next one?
When it's added.
Okay, we changed the timing of when we added things. Okay, so now when I add the ethoxide, what's it going to react with?
The alpha carbons on the other structure.
The alpha hydrogens on our 1, 2, 3, 4 butyraldehyde. Okay, they won't react with the alpha hydrogens on our acetaldehyde. Also ethyl aldehyde, if you wanted to reference it that way. Okay? That's going to limit some of that nucleophilic character so that now really I only have 1 nucleophile. Do I still have some electrophile for both? Yeah. So I'm still going to get 1 nucleophile, 2 electrophiles. That's still going to be 2 products. Okay? How can I make sure that I can get these 2 to react, but very specifically, to form only 1 product? I need to change the conditions. I need to move up the strength of the base. Okay? I need to move up the strength of the base such that the base fully deprotonates the starting aldehyde. Now there's no electrophile left over because that's not an equilibrium reaction. So we end up using the stuff from the tail end of chapter 10, with our enolates and the choice of base on dealing with that. So this last one is now going to guarantee me 1 product, mostly. Okay? Or at least a product with 1 product with a much higher yield than any of the other 2. Does that make sense? Questions about that? Is that a question? No. So, what do we learn from that? Okay, we need alpha hydrogens. Okay, so with that particular reaction, there were no alpha hydrogens. We can't run an aldol reaction. Okay, if I want to do a condensation, an aldol condensation, I need a second alpha hydrogen. Okay, so we need 1 alpha hydrogen to do the aldol. I need 2 alpha hydrogens to do the condensation part of it. Make sense? Okay. When we hit in the crossed system, okay, so when this was initially discovered, it was probably discovered with pure aldehydes. Someone bought some aldehyde reagent, left it in the storehouse for a little bit, maybe it heated up a little bit. They came back and they're like, what the hell happened to this? All this liquid aldehyde turned into a solid. Well, what is this solid? Then they studied it through spectroscopy to see what the end result was. Like, oh, okay, well, that's interesting. What happens, or that happened through this general mechanism we went through. Could I do that with other aldehydes? Could I mix aldehydes? Can I do ketones and aldehydes? So it kind of exploded now that area of doing different reactions. As soon as we do that, we encounter this crossed aldol, okay, which is really just a fancy way of saying I can do it with any ketone I want. Okay? I need to make sure that if I'm going to run the aldol, only 1 species should have alpha hydrogens. This is a reagent control. What am I controlling by making sure only 1 species has alpha hydrogens? Only 1 can be a nucleophile. Okay? Or only 1 species is allowed to control or to enolize. This is looking at our base control. It's still doing the same thing. We're changing the level of the strength of the base to make sure that I get only 1 nucleophile. Both of them are addressing the nucleophile characteristics. Okay? Could we address the electrophile characteristics too? We can if we use species that can only act as electrophiles. Now that's literally the only thing it can do. We're still going to have issues with the nucleophiles. Kind of makes sense? Okay. So what happens if we now move to ketones? And we look at this structure. Okay. Question's a bit misleading at this point, so let's not stress about that question quite yet, I believe. What do you see within that structure?
It's a diketone.
It's a diketone. Why does that make things interesting?
Two different hydrogens that could be cool.
Okay.
Not really?
We have electrophilic sites. And in particular, how many electrophilic sites do we have? Two. If we address the alpha hydrogens, you're right, it has two different alpha hydrogens that could be removed. Where are those alpha hydrogens?
On either side.
Carbon.
Okay, so we're hearing on either side.
No. There's an intermediary planet.
Oh, sorry, on the inside? So you're saying these two hydrogens?
Yeah.
No. That's the same hydrogen.
Okay, so we're getting at different kind of ideas behind this. So now I'm hearing a shift. Oh, well, there's 4 hydrogens. No, he's right. There are only 2 hydrogens that we should really be talking about with this particular structure. There are 4 positions with alpha hydrogens. Okay? 1, 2, 3, and 4. But Mustafa's still right. There's only 2. Why are there only 2?
They're not used.
There's a mirror.
There's symmetry through the molecule, which means the red hydrogens are the same as each other and the blue hydrogens are the same as each other. Okay? Why does this become interesting? Well, if I remove a blue hydrogen, what have I made? I now have a nucleophile. Is there an electrophile nearby?
Yeah.
Where?
The other opposite.
Okay, so I've heard carbonyl, and then I heard other carbonyl, and I like the use of other. What are you saying when you're saying other?
Forming a ring.
You're picking the green carbonyl, not the blue carbonyl. The blue carbonyl is why that hydrogen was acidic. Okay? It's not doing anything other than stabilizing that negative charge temporarily. The green carbonyl now is an electrophile that it could react, meaning we get
Ring.
a cyclic structure. Okay? Couldn't I have removed the red hydrogen? Wouldn't that have been a nucleophile too? Couldn't that also potentially form the ring? Well, yeah. Okay, so there's 2 possible paths we can run. We'll call it red path and blue path. Which pill do you want, right? Okay. Could we choose, by looking at the bases, which one of those paths we'd follow? So Lee, you're saying yes. How would it affect it? If I did sodium hydride, which path would I follow?
LDL is a steric hindrance because of steric hindrance of
It's not steric hindrance.
the
Officially 3 words, though the second word is usually an abbreviation.
Amen.
Yeah.
Why?
Is that a letter or a lesson?
Are you going to spell these properly?
Maybe I would have if you showed up 10 minutes earlier.
Oh. I also want to compliment you on your symmetry, like super symmetrical.
Strength.
A.
Up to the
You gotta put the letter A in there.
Uh-oh.
This is like this one.
I.
You're just using all the vowels.
Oh.
They're very sexy.
Close. Kinetic versus thermodynamic. When we're looking at our bases, it's not a steric argument. It's kinetics versus thermodynamics. Sodium hydride, stupidly strong, favors the kinetic product. LDA,
Also super.
stupidly strong, favors kinetic. T-butoxide,
Not super.
not stupidly strong, favors thermodynamic. The kinetic is the outside one. Why would the outside one go faster?
Because it's
Easier to get to.
In case somebody starts trying to count that. It's easier to get access to. Why is the thermodynamic? I'll accept two answers.
lower energy final.
What's lower energy about it?
It's more stable.
What makes it more stable? What's
The
the
lower or the higher
Higher
activation
activation.
energy to go reverse.
you're just kind of spinning that off the kinetic, which is fine.
The product.
The thermodynamic is lower in energy because it's thermo, and we know it's the thermo one because the other one was the kinetic.
It's longer to get to.
Higher energy.
The enolate that is formed has a more substituted alkene.
Yeah, I was gonna get there.
Okay, it's a more substituted pi bond. The more substituted pi bond is thermodynamically stable. Okay? So we could potentially go through and say, well, sodium hydride is going to give me the kinetic, LDA is going to give me the kinetic, and T-butoxide will give me the thermodynamic product. Guess which product you get for this one?
The kinetic always.
Kinetic only. Why talk about all the bases then? Are there other things that contribute to product formation? Okay, so the kinetic one was the one that we know forms, so let's not look at the kinetic one. Let's look at the thermodynamic. Okay? And Mustafa had an awesome point. This is going to form a ring. Well, how many atoms are in that ring? That can be difficult to see if we just look at the structure. So maybe what we should do is, instead of just looking at the structure, actually label out our carbons.
Oh, I think I have a reason.
1,
It doesn't.
2, 3, I'll come back to you in a second, 4, 5, 6, 7. For those of you going, but that's not in order. It doesn't really matter. This is not a nomenclature system. This is me just trying to number those connections. You notice that I started my numbering where? At the nucleophile, because that's the one that attacks. That's what I have decided for my personal sanity makes the most sense. Okay?
So you get a 4-membered ring.
Carbon 1 needs to be connected to 2, and then 3, and 4. I have 4 atoms in that ring. So I'm going to draw a 4-membered ring. 1, 2, 3, 4.
Versus a 6.
2 and 3 don't have anything connected to them. Position 4 was where the carbonyl was. Remember, I break the bond, I get that negative charge. Okay? Position 4 also has carbon 5 connected to it. Position 1 also has 6 and 7. And sorry, Alex has got me drawing it that way and it bothers me. Sorry. Okay, I want to see those carbons. Okay, 6 and 7. So there we go. There's our answer from the thermodynamics standpoint. Okay, that should already raise some alarm flags, because thermodynamic means more stable, and yet I'm forming a 4-membered ring. That doesn't sound so good. Okay, so what happens if I went through and did the kinetic? Instead of renumbering this, I'll show you that it doesn't matter the numbers. Okay, we're connecting 7, 6, 1, 2, 3, 4, and you might be like, well, I can't count all that. Well, just count it out in your head. 7, 6, 1, 2, 3, 4. There were 6. So that would mean,
Number 7, and there's one number left out.
don't be pulling your math magic on me.
There's a reason he does it.
Okay, 7, 6, 1, 2, 3, 4. Position 4 had the O minus. It also had carbon number 5. Okay, position 6 had the carbonyl. Which of those two drawings is more stable?
The 6-membered ring.
The 6-membered ring. I only get one product regardless of which base I use, which means which base should I use?
T-butoxide.
I should use the safest one. I end up using T-butoxide. Okay? This is an intramolecular aldol reaction. Okay? It still gets classified as aldol even though it is ketones. Okay? Because it's the same base general idea of that chemistry. Make sense? We good? Cool. So, intramolecular. Okay, if we drew that out, you'll notice that here we see the pi bond. If you remember how I drew it out, did I draw the pi bond? Right, 7, 6, 1. God, this numbering's awful. 2, 3, 4, 5. Well, 7, 6, 1, 2, 3, 4. Oh, minus. Yeah? Sorry, it's just a methyl. That's what I drew out. Right? Okay, so we could protonate. There's the OH. We still have effectively our aldehyde. We have a carbonyl in the alcohol. Okay, so it's effectively the aldol, right? Remember, most aldols tend to also do a condensation. Why?
It's more stable.
I'll accept that if we got to our final answer, which is over there.
You have alpha hydrogens.
We still have alpha hydrogens. Those alpha hydrogens are still acidic. And we do the aldol condensation, and we would end with our final answer. Notice the difference is just that we turned the structure a little bit. Everybody see that? Okay. So yes, we can do it intramolecularly, okay, but it can it should only happen if you're forming a 5 or 6-membered ring. Okay? That becomes very tricky when we move into the Robinson annulation, which we might see here in just a second. Okay? There were multiple places that we could have made nucleophiles and multiple electrophiles. How did we know which one resulted in the correct answer? The stability of the product. How did we know what the product was? We drew them out. Let that sink in for a little bit. You have to draw these out. When it comes to the Robinson annulation, there are 4 nucleophilic sites, 3 electrophilic sites. That's a whole lot more chemistry that you've got to deal with. You should draw each and every single one of those possibilities so that you get an idea of how that chemistry is working. Because if you don't, guess when you will find some of those wrong answers? On the exam. Okay? And you'll select the wrong thing. Okay? So I want you to do the practice of getting things wrong and acknowledging that they're wrong. But that usually requires that you have multiple things to choose from. Okay? How many of you like doing things wrong?
Not really.
Yeah, most people hate it. You need to do that in OChem. Okay? You have to push through and do things wrong. The next part of it is also being able to look at it and evaluate why it's wrong. We've done a lot of evaluation stuff. Okay? Virtually everything we've talked about through this semester is evaluating. Did I do something well? Every time you draw something, you need to be asking, what would Mike tell me is wrong about this structure? Okay? And nitpick the crap out of your drawings. Yes?
Why does that not react with the other one? So you've got that one, and you turned into a nucleophile. Why doesn't it react with the second molecule? You have to use
So it could react with a second molecule. That is a possibility, and all of our aldols have that. So as soon as you have multiple possibilities, I believe what you're saying is, couldn't I have reacted this structure with a second one of these?
Yes.
Yes, can happen.
Okay.
The molecule is also large and floppy enough that...
That molecule keep reacting.
that molecule is difficult to react with another molecule.
Okay.
Whereas if we look at its steady state, it's probably going to be mostly folded up on itself. It's going to be easier to react intramolecular than it is
But
cross-molecular.
you still can't get the actual.
You still can get it to happen. You just get lower yields.
And we're gonna keep it.
Yes.
So, like,
Yes.
something where it was like that horrible 4-member ring, and then.
Yep, and let's not make it worse than it already is. Okay, but yes, it can do that. Don't do that. Conjugate addition. Okay, showed up at the end of chapter 17. It shows up at the end of chapter 18 as well. Okay, with the conjugate addition, we're talking about our alpha-beta unsaturated carbonyls. These guys right here. Okay, there's our carbonyl, alpha, beta, yeah? Remember that? And with the alpha-beta unsaturated carbonyls, there were 2 electrophilic sites, which means your nucleophile could either attack at the beta position or directly to the carbonyl. Okay? And that difference was dictated based off of the strength of the nucleophile. If it was a stupidly strong nucleophile, it attacked the carbonyl, 1,2 addition. If it was a weak nucleophile, it attacked 1,4 and it attacked the beta position. Yeah? Remember all that? Okay. If we go back and look at our list from the previous one, Gilman's, we just kind of have to memorize, are 1,4. Okay. Even though we have that stupidly strong negative carbon next to a copper atom, a metal, that difference in electronegativity isn't quite enough, and that makes the carbon a weaker, strong nucleophile. Grignard reactions, stupidly strong nucleophiles directly attack. We get kinetic direct addition, 1,2. Enolates, as far as stability, fall smack dab in between both the Grignard and the Gilman. What's the problem with that? I'm going to get both. If I use an enolate as a nucleophile with an alpha-beta unsaturated ketone, I get both the 1,2 and the 1,4. Which means my yields
Drop.
suck. Okay? And I'm going to have a giant mixture of products. So using enolates in a 1 or an alpha-beta unsaturated ketone is a bad idea. What are we doing in this bottom reaction? So first, right out of the gate, what do we have here? An alpha-beta unsaturated carbonyl. So we are reacting an alpha-beta unsaturated carbonyl, which means don't use an enolate. Where's the reactivity of this molecule? Very first thing we throw at it is
Base.
base. What's it going to do?
Acidic hydrogen.
Pull off an acidic hydrogen to make that nucleophile, which is stable because,
Resonance.
which makes, say that again, Lee. What did I just say do not form?
An enolate.
An enolate. What did we just form? An enolate. God, what the frick, Mike? This isn't just an enolate, though. What is special about this enolate?
Symmetrical.
Symmetrical, which does what to its stability?
Increases it.
That enolate is more stable because of the double resonance. What does that do to the reactivity of that nucleophilic carbon?
Lowers it.
It lowers it. The enolate is smack dab in the middle. But if I have a dienolate, that drops the reactivity just enough that it clears into the Gilman type category and we get 1,4 additions, not 1,2. Okay? So if we go through and look at the result, the bond that formed here, if we highlight that in blue, is right here. Okay? There's the carbonyl, alpha, beta. Where did my enolate attack? The beta position. It did a 1,4 conjugate addition. And it will do that nearly exclusively. Okay? This kind of reaction, because it's kind of this weird, like, well, we shouldn't do it because we get a 50-50 mixture. But if I have this double resonance, no, I don't get a 50-50 mixture. It becomes better. So somebody went through and said, don't do them, and then some jackhole went through and said, but I can do them. Which means there's a name for it. Okay? That name for it, inconveniently enough, after that discussion, is a Michael reaction. Okay? Not me. Okay? It's a Michael addition. Okay? All we're saying is we're forming effectively an enolate, so a strong carbon nucleophile that's not stupidly strong. Okay? And because of that, it will do 1,4 addition. So this one came from, I forget which textbook, but not ours. Okay? They showed a bunch of Michael donors. Why are they Michael donors? They're negative carbons that attack the 1,4 position. Why do I need to call them a Michael donor? Why don't I just call them they attack 1,4? Like they're just freaking nucleophiles. Yeah, I completely agree. Calling them Michael donors is a bit stupid. Okay? It's just, we're naming things for the hell of naming things. Okay? The other ones, these are all 1,4 unsaturated compounds. You'll notice they aren't all 1,4 carbonyls. Right? Carbonyl, 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 carbonyl. That ain't a carbonyl. But if we draw that out, what do we see? We see a polar pi bond. When we're talking about our acceptors in this case, it's an alpha beta unsaturated polar pi bond, not necessarily a carbonyl. Okay? So that's the nitro compound. What's the deal with our nitrile? Alpha, beta, that's still a polar pi bond. So what you're looking for is a polar pi bond and then go one carbon away, alpha, beta. Is there another pi bond there? Yeah, done. You're now talking about doing 1,4 additions, which is your thermodynamic addition. Okay? Which is really just a bunch of factual stuff. I will look... never mind.